Lecture 25 covers sections 4.3 through 4.4.
At the end of today's lecture, you should be able to apply the conservation of energy equation and the conservation of mass, i.e. the continuity equation, to steady-state nozzles, diffusers, and throttles. This will help fortify our understanding and application of the conservation of energy equation to open systems. Before we begin, we have to understand what steady state means. When we say our system is at steady state, we indicate three things. The first is our control volume is fixed with respect to our coordinate frame. That is, our control volume is not translating or rotating with respect to our principal axes. The second is that mass at each point inside our control volume is invariant with respect to time. That is, the mass distribution within each of our devices will not change as a function of time. And last but not least, the state of and mass flux crossing our control surface into our control volume is invariant with respect to time. That is, the time rate of change of mass is identically equal to the time rate of change of energy, which is equal to 0. Therefore, under steady state, our continuity equation reduces to the following. The summation of mass flows into our system is equal to the summation of mass flows out of our system. And our conservation of energy equation becomes the rate at which heat is supplied, Q dot, plus the sum of our mass flows into our system, carrying respective enthalpies, kinetic, and potential energies, is equal to the rate at which work is done by our system, plus the sum of our mass flows out of our system, carrying the respective enthalpies, kinetic, and potential energies. Or on a per mass basis, for a single stream device, a single stream device implies our mass flow in is equal to our mass flow out, Q plus H1 plus V1 squared over 2 plus GZ1 is equal to W plus H2 plus V2 squared per 2 plus GZ2. Now we will begin our analysis of steady-state single-stream devices on a nozzle. Nozzles convert pressure energy into kinetic energy. There's a variety of nozzle designs that you can encounter. Specifically, convergent and convergent divergent nozzles are used when your Mach number is greater than unity.